one? Do you have it with you, or anybody have the problems? Particle free-body diagram. Particle rigid. Rigid body, right? Okay, the last one. Okay, there's a couple of ways you can do this one. Yeah. So the problem looks like this. You have a beam connected to a pin. And then it also has a slot. And there's a pin and slot joint there. And then there's a cable at the end that attaches, or that goes through a pulley and then up to the ceiling. And so the way to think about this is, just decide what you're going to isolate first. There's a couple ways you can do this. So let's say first I just isolate the beam, okay? And now you just apply the weight force. Just call that mg. And then you're just looking around the boundary for places where the body you isolated makes contact with things that you didn't, that are not included in what you isolate. So over here, there's a pin joint. And I think I've sort of stressed this before, but really I think the best way to approach it is just remind yourself that you're not trying to really think about anything. You're just trying to, everything's just like a lookup table. Over here you see a pin joint. So what do you put on the body with a pin joint? It's always just an unknown force vector. And so just put that in like this. And now we get to the pulley. Okay, so this is where there's a little bit of, you can approach this a few ways. Okay, one possibility is that you don't include the pulley in your free body diagram. If you don't include the pulley in your free body diagram, what is the type of joint between that part of the pulley and the beam? Yeah, right. It's just like a fixed joint. So that's going to be, with a fixed joint, you have a full force vector and a couple. So I'll put that in as force on the beam by the pulley vector, and then you also have a couple that I'll call M on the beam by the pulley. And now keep going around the boundary, and the only other, well, no, there's two more places. So the next place that you have contact is the cable applying a force here. So that's like this. And then there's a pin and slot joint. This is the last one. That's going to be, so if the slot is like this, the force is going to be perpendicular to that, one way or the other. We don't know which way, so it's arbitrary which one you choose, but I'll draw it up. And I'll call that RB. That's a scalar variable because we know the direction. Okay, so that's one possibility. The problem with this way of doing it is you have, yes. Mm-hmm. Well, these are all static, so we're always assuming that we know the exact position of the body. That's a possibility. The problem with this possibility is you have a lot of unknowns and you couldn't solve for anything. So you have two variables for RA, two for this force FBP. So we're at 4, 5, 6, 7 variables. So that's a lot. I suppose I think there's no way that we'd be able to solve for this. Actually, we're always going to have too many variables, but 7 is a lot. So now let's do it where we isolate the beam and we include the pulley. So now the outline looks like that. There's a weight force. You still have this pin joint. Keep going around and you run into this pulley. And on the pulley, the outside world makes contact with the pulley in 2 places. Here and here, underneath. Okay. So both of those two forces are going to appear. You know, the thing that I always mention where you could include all the cable from this piece around to this piece with just little bits of cable coming off the end. And then the force always goes right out of that stump of cable. So you have a T there, and then we get around to this other place where the other end of that cable is attached. You have a T there. And then the last force is this RB. Any questions about that one? So doing it this way, we cut down a lot on the number of variables. 1, 2, 3, 4. That's getting much closer to being able to solve. And if we had some way to calculate one of these other forces from an external body or something, then we could just, with one extra equation, we could solve this. So this is preferable to this. But what we have, even though we only have 4 variables, is we have 1, 2, 3, 4, 5, 6 places where we're going to have to calculate the moments and stuff. That's okay. It doesn't take too long. But we can actually cut down on the amount of work if we notice that we could include this strip of the cable in the free body diagram. So this time, I'll isolate oh, this is hideously ugly. Okay. Can you even tell what I'm trying to draw? Dang it. Okay, so there's that. That. It's a little better. Okay, so this time isolate all of this. Okay. Then you have the weight, the pin joint, this cable tension, but now you don't have any cable tension on the other side of the pulley because that's an internal force now. You also don't have a cable force where it connects to the end of the beam because that's an internal force. So that T only appears in one spot. And then you have RB. So this one doesn't change the number of variables from the one right above it, but it changes, reduces the amount of work you have to do a little bit, write out Newton's laws. Any questions about that one? Any other problems about this set of practice problems? Free body diagrams? Who gave me these? How about any other problems? Yep. Okay. Anybody have that one? Particle statics number 5. Yeah, okay. Okay. Yeah, the letter is all screwed up. Okay, so particle statics number 5. That's the one where you have this incline, 20 degrees. And you have a box on the incline with a horizontal force of 50 newtons on it. And the box has a mass of 20 kilograms. And you're just asked to figure out the reaction load. This is static. So Newton's second law, you have the weight, 196.2. You have this externally applied force of 50 newtons. And then you have a friction contact. So we'll just represent that as an unknown force vector. Call that R. And so for part C, you're just going to, use Newton's second law with this, calculate that R. For the next part, you're going to use Newton's third law, just reverse that force, and it gives you the force on the incline. And then the last one, it asks you to break it up into friction and normal forces. We did this, didn't we? Did we do this example? I think this was the one where I mentioned that you could use a rotation matrix for this. The other, so yeah, you could use a rotation matrix that goes from this coordinate system to one that's aligned with the incline. In order to rotate from this to this, that's a clockwise rotation of 20 degrees. So your theta is negative 20. And so your rotation matrix is cosine of negative 20, sine of negative 20, negative sine, cosine. And that is 0.940, negative 0.342, 0.342, 0.940. And then you just multiply that matrix by the vector that you solved for R, and it'll break it up into an X component that gives you the friction and a Y component that gives you the normal force. The other way you could do it, I think the way I did it in the solutions, is you can take the dot products of that R with unit vectors in the direction you want. So take a dot product of R with a unit vector that's parallel to the surface. So that would be 0.940, negative 0.342. And that will give you the friction. You could do an absolute value. I think, it might come out negative. And then the normal force, you'll do that R dot product with a unit vector perpendicular to that surface. So 0.342, positive 0.940. That'll give you the normal. Any questions about that one? And really what you're doing is, if you think about it this way, taking these projections using dot product of your reaction force with a unit vector parallel to the surface and a unit vector perpendicular to it, you can actually see, if you think of how matrix multiplication works, that this is just in two pieces doing exactly the same thing that this does. Because matrix multiplication is just a series of dot products. Oh yeah, sure. Not tensor rotation. You want to just multiply it by a rotation matrix. Yeah, right. And in that case, because you have the deformed version of that rotation matrix, you'll need to write this with a third z component. This will need to be rotated around the z-axis, and this will have to have a 0 at the end. But yeah, you can do it that way. Any other questions from this set? This is particle kinetics. Yeah. Yeah, because it's given in the problem that this is 20 degrees. And the way this rotation matrix works is you have to figure out how you have to rotate. So you don't think of rotating the body, you think of rotating the coordinate system. So to get from the original coordinate system to this one, you have to go clockwise. Counterclockwise is always positive, clockwise is always negative. So you're going clockwise 20 degrees, and since it's clockwise, it's negative 20. Any other questions? Yep. Okay. Do you have it in front of you? No? Let's see. What is yours, David? You did this last time, right? Yes. Yeah. Okay, so I'll draw the free body diagram, but then you can look back at the notes and it should be in there. So rigid bodies. Number 10. So there's the beam, and then it has the cross pieces. And this cross piece has a pulley. And then there's a pulley on the body over here. Okay. And we're neglecting the weight of the body, so there's nothing at the center there. There's 140 pounds acting down here. There's a cable tension, T1, acting there. There's a different cable applying a cable tension T2 in that direction. and a cable tension T2 in that direction. And then where it touches the other pulley, there's another T2 there. And the last T2 is here. And then the last contact is a ball and socket joint with the wall. A ball and socket joint is a full unknown force vector. So in 3D, that's just this. And this one has a place that works out just like one of those first examples I did today. This T2 and this T2, they're forces, same magnitude going right towards each other. And if you think of them as having the same line of action, you can see that you can move one of those T2 forces right to where the other one is without changing the problem, because you can move forces along their line of action. And if you do that, you just get two forces acting at the same location, canceling each other out. And you can see that that's not going to do anything. So you can leave those out, or you could include the strip of the cable that goes between those two pulleys, and then those are internal forces and they don't show up. Or you could do it like that and you'll just see that they cancel out in the end, and you know, nothing's lost there. You just spend an extra minute doing it or something. So, any other questions? All right. Well, the next topic is centroids. So a centroid is a geometric center of an object. We're going to use centroids for two things. The first one is finding the center of mass of an object. So the centroid is the center of mass. As long as the body is composed of a single material. So as long as the body is homogeneous. Homogeneous just means it's the same composition over here that it is over here. So if you have a disc made out of steel, the whole thing's steel, that's homogeneous. If you have a disc that's steel on this side and wood on this side, that's not homogeneous. But as long as the composition's the same at every location, the centroid is the center of mass. And then the center of mass is useful to calculate because the weight, you can always treat the weight like the whole thing is applied at the center of mass. The second thing we'll use it for is for distributed loads. In most of our problem, well, all of our problems so far, I guess, we've treated all forces like they're acting at a single location, just a single point force. But real forces don't do that. Even if you applied a force to an object by pressing down on the back of the thinnest knife that could possibly be made, you know, or the thinnest pointer you could possibly make, still the tip has some finite size. And that force you're applying to the object is still spread over some amount of area. It's just a small area. Okay, so force is really a distributed load. That total amount of force is spread out over some area. And sometimes treating things as if they're acting at a point is reasonable. And other times, the forces are spread out over too big an area for that to be a reasonable approximation. And so we're going to get to problems where we have to take into account how far that load is spread out over. What's the area over which that load is spread? So this is dealing with loads spread over a surface or a surface area. And the problem is, mathematically, we don't really have a way to go straight into Newton's laws with distributed loads. So mathematically, we always have to treat these distributed loads like they're acting at a point. Well, if all you know is that 5,000 newtons is spread out evenly over this plate that you're measuring, how do you know where to apply that point force? And so that's the subject of distributed loads, figuring out where to apply that point force. And that's the second thing that we'll use centroids for. So we need a way to treat these as point loads. And it ends up being that the point load acts at the centroid of the distributed load. Okay. So first I'm going to give you the definition of the centroid, which is an integral definition. And we're not going to really use that in this class, but I'm going to do one example of how to use it. So first is the integral definition. Then later on, we'll just always calculate centroids by using formulas that come from this integral definition. So we're not going to actually do those. So the integral definition of the centroid. First, in two dimensions, the x and y components of the centroid, you represent that with a over bar. So this is saying the x coordinate of the centroid and the y coordinate of the centroid is equal to 1 over the total area times the integral of the centroid of an infinitesimal piece of area times that infinitesimal area. And this is done over the whole area, so I'll call that A. In 3D, it's similar, but you have three components for the centroid. And that's equal to 1 over the volume times the integral over the whole volume of the centroid of some infinitesimal piece of volume dV. I'm not going to do this at all in 3D, so this is the one that we're going to be interested in. Like I mentioned, we're going to be using formulas, like we'll have a formula for a triangular shape, what's its centroid based on its dimensions, for a parabolic shape. And so I want to do one example for a right triangle just to show where these formulas come from. So let's say that we have this right triangle. Where this length is B. And this length is H. And I'll put the coordinate system over here. In terms of B and H, we want to calculate the centroid. So what are the coordinates of the centroid? So we're going to use this integral definition. With any kind of application of an integral definition, the real key to being able to use it is figuring out a good way to break up your total region into these infinitesimal pieces. So like, for example, we're doing a right triangle. If we were doing a circular shape, we might want to try to break it up into infinitesimal pieces of area that are like infinitesimally thin rings around the center. Okay, that's not going to work for a triangular shape. So we need a way to break this up into infinitesimal pieces that make sense for the geometry of the thing. And so I'm going to break it up into strips like this. That's supposed to be infinitesimally thin. Where the location of that strip, that arbitrary strip, is X. The thickness of that strip is dx. And the height of that strip, the height of that rectangle, we can get from an equation for the line of the hypotenuse. So can you come up with an equation for a line that represents the hypotenuse of that triangle? So we're going to do like y equals x plus b. Yeah, very good. Yep. The slope of that is the rise over run, so h over b times x, and then add on the y-intercept. Well, at the y-axis, or at the y-axis, the y value is 0, so there's no y-intercept. So this is hx over b. Okay, so we're going to be dealing with these. We're adding up all these rectangles that have a thickness of dx and a height of hx over b. Okay, so let's go to this formula. The total area of the triangle is just BH over 2. And so now we'll go to the centroid formula. X bar, Y bar is equal to 1 over the total area. So that's 2 over BH. Times the integral over the whole area of, now we're dealing with these strips. So the integral definition says in the integral, we're adding up for each one of these infinitesimal strips, the centroid of that strip times the area of that strip. Well, what's the x position of the centroid of that strip? Just x? Yep, that's exactly right. And what's the y position of the centroid of that strip? Remember, for a rectangle, the centroid is just right in the middle. So the centroid is right here. If the total height, the total y, like the y position at the top of this rectangle is hx over b, then this is going to be hx over 2b, which is half of that height. So the centroid of that strip is x, and then hx over 2b. And then we're multiplying that by the area of that strip, which is hx over b times dx. This here is the centroid. This is dA. Any questions yet? And since our variable, now we've represented everything in terms of x, the boundaries for this whole region are just going to be x values from 0 to b. So I'll put that in the boundaries. And I can rewrite this. So 2 over b times h times the integral from 0 to b of hx squared. I'm just multiplying all of this through. Hx squared over b times dx. And then for y, h squared x squared over 2b squared. Dx. And now we're just integrating both of those two components with respect to x. So we get 2 over bh times, if we integrate the x component with respect to x, we get hx cubed over 3b. And the y component, we get h squared x cubed over 6b squared. And that's evaluated from 0 to b. And now plug in the boundaries, and you get 2 over bh times the vector. The x component here is h, it's on h b cubed over 3b. And the y component is h squared b cubed over 6b squared. And you can simplify that. So let's see. We end up with 2b squared, and that one more b goes away, so we have 2b over 3 for that one. And for the y component, we have h over 3. Okay, so that was just like a lot of algebra. The main idea is just to understand how you use this integral definition. And if you don't want to, you really don't have to, I guess. We're not going to do any problems like that. I don't think. There might be one, but I don't think there's any. But the take-home message is for a right triangle, if this is B, and this is H, then the centroid is along the x direction. What we saw was that this distance is 2/3 B, and that means this distance has to be B over 3, the one that I drew here. So this is B over 3 from the centroid to the end. And then the y component, we got that this distance is H over 3. And now that we've gotten to this point, we don't ever have to use that integral definition for a triangle again. We can just use these formulas. We know that whatever this distance is and whatever this distance is, and if you think of each side, each leg, as starting on one side like a wall and at the other side a point, you're always going 1/3 of the way from the wall to the point. Okay. So before I give formulas for all the shapes that we're going to use, I need to say one important thing about centroids. So here's an important fact that often simplifies centroid calculations. In 2D, the centroid always lies along any line of symmetry. So like, for example, if you want to find the centroid of a shape like this, or a shape like this, for the first one, there's a line of symmetry, a vertical line of symmetry like this. So the centroid has to lie somewhere on that dotted line. And for the second one, there's a line of symmetry like this, horizontal. And so the centroid has to lie along that somewhere. And so if you can find any line of symmetry, you can cut down the number of centroid calculations you have to do. You know, like in this case now, we no longer have to calculate the x component of the centroid. We just have to calculate the vertical component. And this one, we have to calculate the horizontal component, but we don't have to calculate the vertical component anymore. And also, if you can find two lines of symmetry in a body, then the centroid has to lie at their intersection. So for example, we've done a lot of rectangles, and we've always just sort of glossed over the centroid calculation and just said the weights apply to the middle. Well, the reason the middle is the centroid, you can think of it in terms of lines of symmetry. There's a horizontal line of symmetry like this, a vertical line of symmetry like this, and so the centroid has to be right there. For an ellipse, ellipses are hard to draw. Okay, you know what I'm trying to get at there. There's a vertical line of symmetry. And a horizontal. So the centroid's right there. And then for a circle, there's infinitely many lines of symmetry. No matter which two you choose, they intersect at the center. And so the centroid has to be right at the center of the circle. So what that says is for any body where you can find two axes of symmetry, we don't even need a formula to calculate where the centroid is. You just put it right at the middle. Any questions about that? By the way, so this isn't going to be something that we use in this class, but in 3D, a line of symmetry doesn't have the same meaning that it does in 2D. So in 3D, the centroid lies along any plane of symmetry. And if you can find three planes of symmetry, then they meet at a point, and that point is the centroid. So three planes of symmetry. Okay, so now I'm going to list out 5 shapes that we're going to use. So these are the centroid formulas for 5 common 2D shapes. There's a PDF on D2L that gives all these formulas. So, you can look them up anytime. Centroid formulas for common 2D shapes. And so I'm going to do it sort of like a table. Here's the shape over here. Here's X bar, Y bar, and then the area calculation. Okay, so the first one is a right triangle, and we actually derived that formula. So if this is, let me move that down. Okay, so if the width horizontally is B and vertically is H, and in either of those two directions, you can always think of this as going from, it sounds like from a kindergarten way to describe a triangle, but I can't think of any better words. But it always goes from a wall to a point, okay? You go one way, you get to the point, you go the other way, you get to the wall. And so, and it's true going vertically too. Here's the wall and here's the point. So the centroid is always 1/3 of the way from the wall going towards the point. So I'll call this distance x bar, and this distance y bar. R is equal to b over 3. Y bar is equal to h over 3. And the area is bh over 2. I want you to notice something about the coordinates of the centroid. These are just, so in the definition that I gave before, x bar and y bar are coordinates of the centroid. But notice that here, these are just distances. And so, like, if you had a coordinate system in this corner, you know, and you wanted to give the coordinates of the centroid in this coordinate system, you'd go x bar, you know, b over 3 in the negative x direction to get here. And you'd go y bar in the positive y direction, h over 3, you know, vertically. And so the coordinates would be negative b over 3, positive h over 3. And sort of the main trick for using these formulas, the main thing that you have to get comfortable with, is using these distances in whatever coordinate system you're in to figure out what the coordinates are of this point. Okay, so just think of these as distances, but you're going to have to turn those distances into coordinates.
I think it would be really nice to flip the triangle
Mhm.
and have the x, y axis.
That would be. It would. It does seem that way, but I don't know. You'll have to do it yourself. But like, no matter how I show it right now, you're going to have problems where you're going to have to mentally flip it around backwards or upside down or whatever. So you're just going to have to get, you know, comfortable doing that. The second shape is a semicircle. So this distance is r, the radius of the circle. There's a line of symmetry, and so we know that that x bar is, you know, along this dotted line, but y bar is up here somewhere. And so this distance is, so that x bar comes from symmetry. The y bar value is 4r over 3 pi. And then it's half a circle, so the area is pi r squared over 2. The next shape is a quarter circle. And this one has a radius r. This also has a line of symmetry. And so we know the centroid has to lie along that line of symmetry. But I'm going to give you formulas for x and y, so you don't have to, you know, so you don't have to calculate how far you go along that 45-degree line. So I'll call this distance x bar, and this distance y bar, and they're both going to be the same. So x bar, excuse me, is 4r over 3 pi. Y bar has to be the same thing, 4r over 3 pi. And then the area is just the area of a circle divided by 4. So pi r squared over 4. There's 2 more. The fourth one is a parabola. A parabola has a line of symmetry down the middle. And so let's call this distance h. And this distance, oh no, it's actually half of that distance, we'll call a. And the centroid has to be along that line of symmetry. So we're just looking for pi bar, this distance. Okay, so the x bar just comes from symmetry. The y bar is equal to 3h over 5. And the area is 4ah over 3. Let me know if I'm going too fast or anything. And then the last one is half a parabola. So, like this. And I'll call this distance a again. And this distance h again. And the centroid's going to be over here. So this distance is x bar. And ooh, you know what? I messed something up on the I drew this y bar in the wrong like the that should actually go from the tip of the parabola to the centroid. Sorry about that. So the y bar on the parabola is like the complement or whatever of what I had. The formula is right. And then for the half parabola, same thing. It goes from the point to the centroid. Then x bar is 3a over 8. Y bar is 3h over 5. And the area is 2ah over 3. It's half of the other area. Any questions about any of those? So, I mean, there's not too much like understanding with this. It's just formulas that you could get if you wanted to try to grind through those integral formulas, those integral definitions. And I'll do a couple of examples of how to use these. One more thing I want to say be important for using centroids. So this is building up complicated shapes from simple shapes. Okay, so I'm going to, so you can, so let's say if a complicated shape can be broken up into n simple shapes, then the centroid of the complicated shape, x bar, y bar, is equal to 1 over the total area times the sum over all of the simple shapes, so for from I equals 1 to n, of the centroid of the ith simple shape times the area of the ith simple shape. And it works with subtraction too. So I'll do examples of both of these. Okay, so the first example, let's say that we have sort of a T shape where across the top it's 0.2 meters. And the thickness across the top is 0.1 meters. And then there's a narrower vertical part with a thickness of 0.05 meters. And a height of 0.2 meters. I'm going to put the origin of the coordinate system at the bottom, right along the line of symmetry. And we want to calculate the centroid. What are the units of the centroid? Well, you can see that there's this line of symmetry. And that cuts down the amount of work we have to do. What do we know, the vertical location of the centroid or the horizontal location? Yeah, so we know the horizontal location. Now we just have to figure out the height of the centroid. So y bar is equal to, I'm sort of getting ahead of myself. So let's break this up into two pieces. We'll break it up into the top piece and the bottom piece. I'll call this 1 and this 2. And the coordinate system's down here. So piece 1, the area is 0.1 times 0.2, 0.02. What's the vertical location? What's the y bar just for that piece 1? So it's, if you go from the origin up 0.2, you're here, and then you have to go up another 0.05 to get to the center of that rectangle. So 0.25. So y1 bar is equal to 0.25. And then for piece 2, the area is 0.05 times 0.2. So that's 0.01. And what's the height of the centroid of piece 2? And then what's the total area of the shape? 0.03. Yep. So the sum formula says the y centroid is equal to 1 over 0.03 times the centroid of piece 1 times its area. So that's 0.25 times 0.02 plus the centroid of piece 2 times its area, 0.01. And if you do that calculation, you get 0.2. X bar is 0 just because of the symmetry. So x bar, y bar, the coordinates of the centroid of this whole thing is 0.2. Any questions about that one? I'm going to do a subtraction one. This will be fast. Okay, so let's say we have a shape like this, where let's say this is 1, this is 2, this is 1, and this is 0.5. And we want the centroid. Well, I'm going to break it up into, you could do this as 2 rectangles added, but I'm just going to show how to do it as a rectangle removed from a bigger rectangle. So I'm going to set this up as a big rectangle minus a little rectangle. And so the big outer one is 1, the little inner one is 2. And let's put the coordinate system in this corner. Okay, so for rectangle 1, the area is, it has a height of 2 and a width of 1, so the area is 2. The centroid is x1, y1, 0.5, 1. Rectangle 2 has an area of 0.5 and a centroid location of 0.75 for x and 1.5 for y. And what's the total area for this one? For the whole thing, so you have to subtract the areas. The area that we want for the total is just, the material. So the total area is going to be 2 minus 0.5, so 1.5. And then the centroid is 1 over 1.5 times the centroid of piece 1, so that's 0.51, times its area, minus the centroid of piece 2 times its area, minus 0.75, 1.5 times 0.5. And let's see, that's 1 over 1.5 times 1, 2, minus 0.375, 0.75. Can someone calculate that? Okay. 0.834. Okay. Thank you. Any questions about that? Okay, that's it.